In this video, we will begin discussing solving trigonometric equations. We start with a general discussion of solving such equations and then consider 4 specific examples to illustrate the techniques. Let's first review what we know about trigonometric equations and functions. A trigonometric equation is simply an equation involving trig functions. Recall that to solve an equation means to find all values of the variable that make the equation true. Since the period of the sine and cosine functions is 2 pi, we know that sine values and cosine values repeat every 2 pi units. Similarly, the function values repeat every pi units for the tangent function. In fact, all of the trigonometric functions are periodic, so any solutions to a trig equation will be repeated in each period. Thus, the equations will have infinitely many solutions. Often, we will be asked for all solutions in a particular interval, usually the closed interval from 0 to 2 pi. Typically, we will find all solutions first and then list the ones in the given interval. We will illustrate this in our examples. Let's solve the equation sine x equal a half. We want to find all real values of x that satisfy the equation. From our knowledge of the unit circle, we have the following. Positive values of sine occur in the first and second quadrants, and x equals pi sixth and 5 pi sixths have sine values equaling a half. These are the values that are the solution in the interval from 0 to 2 pi. All possible solutions are given by x equals pi over 6 plus 2k pi and x equal 5 pi over 6 plus 2k pi, where k is any integer. When the instructions simply say solve the equation, the default assumption is that we want all solutions, including all periods. In example 2, we are asked to solve -2 times cosine x equal to for x in the interval from 0 to 2 pi. This time we will write the solution similar to that of solving any algebraic equation. We start with the given equation. Then divide both sides by -2. We have that x is the angle whose cosine is -1. In the interval from 0 to 2 pi, we know that cosine x equal -1 when x is pi. This is the only solution in the given interval. Let's repeat the problem with the directions to solve -2 times cosine x equal 2. Now we want all real valued solutions to the equation. We again start with the given equation and divide both sides by 2. This time, we specify that cosine x equal -1 when x equals pi plus integer multiples of 2 pi, picking up the solutions repeated by period. If we factor out pi, we see that cosine x equals -1 at the odd multiples of pi. Let's consider a similar problem and solve the equation cosine theta equals 0. Although this problem looks very similar to the previous one, there are some important differences we must consider. We start with the given equation, and we could write that theta equals the inverse cosine of 0, but the inverse cosine function will only produce one value. That's the very definition of function. The inverse cosine function will always produce outputs between 0 and pi. So we have to manually insert those values in the third or fourth quadrants, as well as any repeated values in other periods. It would be nice to write these solutions more compactly if possible. We get common denominators and notice that plugging in k values starting at k equals 0 produces the x values of pi halves, 3 pi halves, 5 pi halves, 7 pi halves, etc. These solutions amount to the odd multiples of pi over 2. Let's consider one final example to solve the equation 2 minus 2 cosine theta equal 3 for theta in the interval from 0 to 2 pi. We have our original equation and can subtract 2 from both sides. Now we divide both sides by negative 2. Now we want theta in the interval from 0 to 2 pi, for which cosine theta is negative 1/2. Those values will be in the second and third quadrants. From our knowledge of the unit circle, we get that theta equals 2 pi over 3 and 4 pi over 3.